Hey everyone, and welcome to our deep dive today. We're going to be looking at some pretty fascinating stuff, all about synthetic data and its impact on the future of AI. I mean, it's one of those things that can be kind of alarming too. So to walk us through all of this, we've got an expert with us.
Happy to be here.
So, when we think about AI, I think
Mhm.
one of the things that comes up is this idea of like training models.
Right.
So imagine training an AI using data that was generated by another AI.
It's definitely a question a lot of researchers are grappling with, and there's a paper we're looking at called How to Synthesize Text Data Without Model Collapse.
Okay.
Really dives right into this. Looks at a concept called non-iterative model collapse.
Okay, now hold on. Non-iterative. So is that different from the regular type of model collapse?
Yeah, the kind we usually hear about is referred to as iterative model collapse. And that's where a model's training repeatedly on its own output. You get sort of this feedback loop that happens.
Right, right.
But this non-iterative version, and this is described in the introduction of the paper in section 1, it's more about the effects of using synthetic data from a different AI for training.
Hmm. So, thinking about the future of AI, if we're trying to build these powerful AI systems, does that mean we can't even really use this approach to train them?
Well, that's what the researchers set out to investigate. And they took this really structured approach,
Okay.
starting by pre-training language models with a mix of synthetic and human-generated data. And they detail this all in section 4.1 in the experimental setup.
Okay, so did they basically just, like, feed the AI a ton of synthetic data and just see what happened?
Essentially, yes, but they did it in a very systematic way,
Okay.
carefully documenting how things changed as they increased the proportion of synthetic data. And what they found was actually pretty concerning.
So I'm going to guess here. Did the AI, like, get worse the more synthetic data they used?
You're on the right track there. If you take a look at figure 2 in the paper, you'll see a bunch of graphs that really show this trend.
Okay.
They used a measure called perplexity to see how well the model could predict text. Basically, a lower perplexity score means the AI understands language better.
Okay.
And as that percentage of synthetic data went up, that perplexity score also went up.
So the AI was basically getting worse at understanding.
Yeah, you could almost say it's like the AI was only ever given like really simple children's books to learn from.
Hmm.
And then suddenly it's asked to, understand some super complex piece of literature. It just wouldn't have the tools to do that.
So it's like it's getting a simplified version of reality.
That's a good way to put it. But what's interesting is that the researchers, they didn't just stop there. They wanted to figure out why the synthetic data was performing so poorly.
Okay, so this is where, like, the real detective work begins.
Exactly. They analyzed that synthetic data from a few different angles. They explain this in section 4.2, which is the analysis of model collapse from synthetic data.
Hmm.
And one of the things they found was this issue of coverage collapse.
Okay, coverage collapse. What's that about?
Well, to understand that, take a look at figures 3 and 9 in the paper. Those figures show how the perplexity scores are distributed for both human and synthetic data.
So I'm looking at these figures and I'm seeing a pretty big difference here. The human data is all spread out, right? It's got some values way out on the higher end of the scale. But the synthetic data, it's all kind of bunched up on the lower end.
And that right there, that's coverage collapse in action.
Yeah.
The synthetic data is missing that range, that breadth and depth that we see in human language. It's missing those unique outliers, that unusual phrasing that makes human communication so complex.
So it's almost like the synthetic data is a sanitized version of reality.
Yeah, you could put it that way. And on top of that, the researchers found another problem, an over-concentration of what they call n-gram features. They covered this in section 4.2.1 on coverage collapse.
Okay, now remind me, what are n-gram features again?
Essentially, they're sequences of words. So a 2-gram would be like 2 consecutive words, 3-gram is 3, and so on. And what they found was that the synthetic data was overusing certain combinations of these n-grams, making it much less diverse compared to the human-generated data.
Got it, got it. So it's not just about missing words, it's about how those words are actually put together.
Yeah, exactly. And they actually tried to fix this problem using something called DSIR
Okay.
to try to filter out what they called bad synthetic data.
Now, DSIR, that rings a bell. Remind me what that is.
It's a method, and they describe this in Appendix B, for selecting data that closely matches a target distribution. In this case, they wanted to select synthetic data that was more similar to the human data.
And did it work?
Not really, no. Even after applying DSIR. If you look at figure 4, you'll see that the selected synthetic data still looked quite different compared to the human data.
Huh. So it seems like they hit a roadblock there.
Mm.
Like synthetic data just has these built-in limitations, and even with, fancy filtering, you can't totally overcome them.
Right.
But I'm guessing the story doesn't end there.
You're right about that. They actually came up with a pretty interesting solution that they call toe edit. And this is described in Section 5, toe edit, token level editing.
Go edit. Okay, I'm intrigued. Tell me more.
So instead of generating synthetic data from scratch, toe edit starts with human-generated data.
Okay.
And it uses AI to make edits, but it does this at the token level.
Now, hang on. When you say token, what does that mean in this context?
A token can be a word or even just part of a word. Think of it as the smallest unit of meaning that the AI is working with. So what toe edit does is it looks at how likely different tokens are to appear in a sequence. And if a token is highly predictable, meaning the AI is pretty much certain what it should be, toe edit will resample that token.
So they're basically introducing a bit of randomness to shake things up.
In a way, yeah. And the whole process is super efficient because it's what they call non-autoregressive. It's in Section 5.1, non-autoregressive token level editing.
Okay.
It doesn't have to go through the text and generate things one after the other. And they have a nice visual representation of this whole process in Algorithm 1.
Okay, so this toe edit thing, it sounds pretty impressive. But does it actually work?
That's the real test, right. And they ran a bunch of experiments, and the results were actually really promising. If you look at tables 2, 3, and 4 in the paper, you'll see how it all breaks down.
So looking at these tables, it seems like across the board, this toe edit thing is doing better than models trained just on human data.
Wait, did they actually manage to beat the performance of real human data?
It looks that way. Wow. Okay, so this is a lot to take in. We've covered a lot of ground already, and it feels like we're just kind of scratching the surface of this whole synthetic data thing.
Yeah, there's definitely a lot more to unpack here.
Before we move on, though, I want to kind of go back to this idea of synthetic data itself. It seems like there are like different types of synthetic data, different levels maybe.
That's a good point. The paper actually gets into that. They talk about the difference between what they call pure synthetic data and semi-synthetic data. And this is in Section 3, synthetic data. So we've been talking about this pure synthetic data, right, that's generated entirely by a language model from scratch.
Okay.
But then there's semi-synthetic data, which involves taking existing human-generated data and kind of modifying it.
Okay, so how do we know like what's pure and what's semi-synthetic? Is there like a specific way they define that?
Yeah, they actually define it based on how much the synthetic data's distribution diverges from that of human-generated data. They use something called KL divergence to measure this.
KL divergence. Now, I'm not super familiar with that term.
It's a mathematical concept, but basically it measures how different two probability distributions are from each other.
Okay.
So if the KL divergence between the language model's output and human-generated data is above a certain threshold, they say that output is pure synthetic data.
So if it's really different from human language, then it's pure synthetic.
Yeah, and semi-synthetic data would be below that threshold since it's still rooted in human language.
Makes sense. So like examples, what would be an example of pure synthetic data?
So Cosmopedia, which we talked about earlier, that would be considered pure synthetic data.
Cosmopedia, okay.
Because it's generated by the model without directly modifying any human data.
Okay, pure synthetic. And what about semi-synthetic? Aside from this toe edit thing, is there another example?
Yeah, they mention a method called rephrasing the web. And basically this involves using a language model to reword or paraphrase existing human-generated text. So you're generating data that's kind of similar to the original, but with some variation.
So it's like taking, say, a human-written article and having the AI rewrite it in like a different style or voice.
Kind of like that. So both toe edit and rephrasing the web would be classified as semi-synthetic data because they're refining or adapting human language.
And this whole distinction between pure and semi-synthetic, this seems pretty important, right? Because we've seen that pure synthetic data can lead to problems like model collapse.
Right, and that's one of the reasons why this toe edit thing is so interesting. It's like, it's a way to use the power of AI to generate good data for training, but without straying too far from the complexities of human language.
It seems like a pretty big deal, potentially.
Definitely has a lot of potential there.
Okay, so let's dive back into TOEdit then. Can we get a little more specific about how it actually works? Like, how is this different from traditional methods of data synthesis?
Sure. So traditional methods, they usually involve a language model creating brand new data based on a given prompt. Like you might ask it to write a story.
Okay.
And that often leads to what we've been talking about, this pure synthetic data.
Right, with all those
But
limitations.
TOEDIT, it takes a different approach. It's not about generating something totally new. It's about modifying what's already there.
So instead of writing a news story, it's more like editing an existing story.
That's a good analogy. And this difference is really important because by working with human-generated data as a starting point, TOEDIT is able to preserve a lot of the nuances, the complexities of human language.
Okay, I'm following.
Hmm.
But how does it actually make those edits? Like, what's the process?
Well, it uses a pre-trained language model to analyze the probability distribution of tokens in the human data. And they found this really interesting pattern, what they call a U-shape distribution, and you can see this in figure 6.
U-shape.
Yeah, and they explain this in section 5.2, the theoretical analysis. Basically, it's all about how the probabilities of tokens are distributed.
Okay.
And what they found was that the tokens with very high and very low probabilities, those are the ones that are most concentrated.
So a lot of the tokens are either super predictable or super unpredictable.
And that's where TOEDIT comes in. It focuses on the tokens with high predictability,
Okay.
the ones that are above a certain threshold, and
Yeah.
they set that to 0.99. So those are the tokens where the model's pretty much certain what it should be.
Right.
And what they do is they resample those tokens based on their conditional probabilities.
So they're adding in like a calculated amount of randomness.
Yeah, you could say that.
Yeah.
And because TOEDIT doesn't generate text one token after another, it can do this pretty efficiently. It uses a non-autoregressive approach, so it doesn't have to predict those tokens sequentially.
Okay. This all sounds very promising. But before we get too carried away, what about the theory behind all of this? Did they actually, did they back up their claims with, any math?
They did. So to really understand the theoretical foundation of TOEDIT, you have to look at how they analyze the test error.
Okay.
They actually adopt this linear model framework, and it's similar to what's used in studies of iterative model collapse.
So they're using a simplified model to represent this complex phenomenon.
Right. That's pretty common in theoretical analysis. It helps to focus on the core principles without getting bogged down in all the details of, real-world language models.
Okay, and what did their analysis show?
The main finding, and they state this in Theorem 2, is that the test error of TOEDIT is bounded.
Okay.
Meaning, no matter how many times you apply TOEDIT, that error isn't going to just keep growing out of control.
So it's not like this runaway train of errors.
Exactly. And that's different from iterative model collapse, where that error, it accumulates with each iteration. They have that in equation 8.
So TOEDIT, it basically avoids that whole issue of error accumulation, which is a big part of model collapse.
Right. And the reason for that, according to their explanation, is that TOEDIT preserves the coverage of the original human data distribution. It's not making huge changes to the data. It's just refining it.
That's pretty cool. So it's working within the boundaries of human language, so it doesn't run into those same problems.
And that theoretical foundation really strengthens their argument for why TOEDIT is so effective.
So we've got this, promising technique, and it's backed by this solid theoretical framework.
Right.
I'm definitely ready to hear about the experiments now.
Okay, so the theory is important, but you really have to see how it works in practice. And to test TOEDIT, they ran a whole bunch of experiments, and this is all in section 6 experiments, across 3 main stages of language model training: pre-training, continual pre-training, and supervised fine-tuning.
3 different stages. That's pretty thorough.
They wanted to make sure that TOEDIT could perform well in different training scenarios.
Makes sense. And for these experiments, they used a language model called Llama 3.8b, right?
Yeah, Llama 3.8b was their main one, but they also used OLMA 1b for some of the experiments. They described this in the setup in section 6.1.
Okay.
And they evaluated these models on a whole range of downstream tasks like question answering, text summarization, code generation.
So they really put it through the ringer.
They did. They even experimented with different resampling thresholds and different sampling strategies to try and optimize TOEDIT, and that's in section 6.2, main results.
This is all really fascinating. So did it actually live up to the hype? Did TOEDIT actually work?
Well, if you look at the results summarized in tables 2, 3, and 4, they're pretty clear. Across all three stages of training, toe-edit consistently outperformed the models that were just trained on human data.
So they actually did it. They made a synthetic data method that works better than real human data.
The results point in that direction, yeah.
I know we're getting short on time, but can we talk a little bit about those ablation studies? Those were the experiments where they kind of tweaked toe-edit, right? To see how it all worked under the hood.
Yeah, they wanted to figure out what factors were really driving the performance of toe-edit.
Okay.
So, for example, they tested different values for the resampling probability, which they call P. And they talk about this in section 6.3, ablation studies.
And what did they find?
Well, if you look at table 7, you can see that the value of P actually did have an effect on performance.
So you gotta find that sweet spot.
Right. And they also tested different sampling strategies, which you can see in table 5. In the end, they found that top case sampling worked best.
And remind me, top case sampling, that's where it picks the K most likely tokens.
Yeah, exactly. So basically, they fine-tuned toe-edit to squeeze out the best possible performance.
This has been a really eye-opening deep dive.
Yeah, definitely a lot to think about.
I feel like I've gotten a much better grasp on this whole synthetic data thing. You know,
Yes.
the challenges, the possibilities.
There's always more to learn, too.
Oh, I'm sure of it. I mean, we've just barely scratched the surface here, but I think we've given our listeners a lot to chew on for now.
Yeah.
Yeah, we've definitely gone deep on this one.
It's a really exciting area of research, for sure.
So as we start to, wrap up our deep dive here, I'm kind of left wondering, if we can make synthetic data this much better with this toe-edit thing, what else is out there? What other kind of cool innovations might be coming down the line?
That's a really great question, and I think it really speaks to, just how much potential there is in this field, even in the paper itself. In the conclusion, section 7, the researchers, they talk about a few different areas for future work, like exploring, different editing strategies,
Mhm.
or looking at how toe-edit works with other types of language models.
It really does feel like we're just starting to understand, what we can do with synthetic data.
Oh, yeah, absolutely. This research, it really opens up all sorts of new possibilities for, creating and using synthetic data. And I'm definitely excited to see where things go from here.
Well, I have a feeling this won't be our last deep dive into this topic. I mean, as this field keeps developing, I'm sure there'll be plenty more for us to talk about.
Looking forward to it.
Well, thanks again for joining us on this journey into the world of synthetic data.
It was my pleasure.
And to our listeners, thanks for diving in with us. We'll catch you next time for another exploration of, well, some more groundbreaking ideas